Good afternoon. My name is Zvonimir Bandik, and I'm chairman of CHIPS Alliance, member of the board of directors of RISC-V, and a senior director of Next-Gen Platform Technologies Department in Western Digital. My area of focus is RISC-V core design, RISC-V design verification, RISC-V firmware toolchain, and on the more research side, designs of low latency memory controllers, machine learning accelerators, and new interconnect ideas such as OmniXtend, which is an open source cache coherence over Ethernet technologies that I'm going to talk about today. On the agenda, I'll have first few words about the CHIPS Alliance organization. Then I'll proceed with the details on OmniXtend cache coherence over Ethernet architecture. And finally, I'll follow with the next steps. So first, a few words about CHIPS Alliance. CHIPS Alliance is an organization which develops and hosts open source hardware code. Think IP cores such as RISC-V CPU cores or machine learning and neural network inferencing IPs. Then a lot of open source software design tools, which is the fastest growing component. This covers very mature tools like Verilator or Fuse SoC, and revolutionary new open source tool chains like OpenRoad, which is a fully open RTL to GDS architecture. And we also cover interconnects IPs, which attracts a lot of interest. We have a AIB chiplets interconnect IPs. We have tiling cache coherence protocol. We have OmniXtend cache coherence over Ethernet. CHIPS Alliance is a barrier-free environment for collaboration that follows standards organization framework for collaboration and focuses on Apache v2 licensing model for the legal framework. The idea, obviously, is to share resources, dollar and time, to lower the cost of hardware development for IP and for the tools. CHIPS Alliance, who are we? This is a list of growing list of our members. We have over 15 members, including Google, Intel, Western Digital, Sci-Fi, Esperanto, and UC Berkeley, who are on the board, and Alibaba, who are on the board of directors. In terms of the active work groups, we have a Chisel work group that's the largest work group focused on a Chisel toolchain, AI accelerator group that's just starting, tools work group that has many interesting tools like Verilator, FuseSoC, CocoaDB Verilator integration effort, cores work group that has Swerve cores from Western Digital, which we talked about on the last RISC-V summit, and interconnect work group with projects like OmniXtend, which I'll talk about today, Tilink, and AIB chiplets interface. So now some details about OmniXtend. First, why OmniXtend? Why bother at all? In the present day compute architectures, processor acts as a main control point in the data center. And as we are embracing new world of compute acceleration with the growing role of dedicated compute accelerators, which could be a GPGPU cards or FPGA-based boards or dedicated AI accelerator silicon, we find its memory block behind the processor. There's a limited number of DIMMs per socket, a limited CPU memory address space, and all the main accesses have to be done through a CPU. So this is actually driving new ideas into how to attach accelerators. And there's many ongoing closed and open architecture efforts directed into sort of improving I/O and memory accesses. So how does OmniXtend differ from other memory-centric concepts? Certainly, it's not a new idea to try to improve memory accesses. And Western Digital has been over the years involved in many efforts, and members of CHIPS Alliance are familiar with many efforts, such as a RDMA-based networking, which is a mature technology that brings memory accesses over Ethernet using remote DMAs. Then there have been very novel architectures like Gen Z that bring load and store accesses across a global memory fabric. And these architectures have some pros and some cons. Some of the issues were related for RDMA networking with the context switch cost, which is fairly large. Or in the case of load and store architectures, need to do a lot of applications rewriting. In the case of OmniXtend, we sort of went back to the past and decided to actually do a cache coherence protocol scale out over Ethernet. And this allows minimizing impact on application system call interface. There's no need to rewrite applications. There are some changes to the boot process needed, and we discussed these software topics in a presentation by Atish, Patra, and Tu Deng on OmniXtend on Tuesday. So OmniXtend, it's a really open unified memory fabric that brings together RISC-V processor, potentially other processing technologies supporting the same protocol, and obviously GPU, AI, and FPGA-based accelerators. And puts memory in the center of the architecture, meaning all these devices can access the same memory over the Ethernet, ubiquitous Ethernet fabric using the same protocol. We have partnered with Sci5 on prototyping this technology, and we leverage the open source styling protocol that came from the Berkeley. It's a cache coherence and a bus protocol. And we took advantage of the existing tiling IP on Sci5's SoCs, and we encapsulated and serialized tiling messages and transported them over Ethernet. This is basically the sort of high-level block diagram of the implementation. We post the last level cache miss. We take the cache coherence messages and we serialize them for consistency over Ethernet. And then we use ubiquitous Ethernet, which is a low-cost IPs, the cabling, the Ethernet switches to build out the architecture. The benefits are clear. We are completely unleashing memory from the CPU. There's no need to rewrite application software, or certainly no significant rewrite. It's based on a low-cost Ethernet, which is really great from perspective of building ASICs or leveraging cabling and leveraging switches. We do already have FPGA implementation that's fairly mature. This is really the only completely open cache coherent fabric standard that we are aware of. And it enables many interesting new data-centric architectures, including building a very low latency memory appliances for compute clusters. So this is the block diagram of the OmniXtend architecture. We are basically showing two RISC-V nodes here. Each node has 4 RISC-V hearts. And cache coherence serializers are generating tiling messages after last level cache miss, and they send them over the Ethernet. And in some architectures, we use Tofino programmable switches just to have more fun with switching. But actually, off-the-shelf Ethernet switch will work just fine as well. Programmability is not required. It's just interesting from innovation perspective. Our interest in Western Digital is really taking advantage of this architecture and building a specialized OmniXtend nodes that will focus on providing many tens of terabytes, if not petabytes, of very low latency persistent memory over OmniXtend fabric. This will mean that you can build a very powerful RISC-V compute clusters for data center and edge, and add a significant amount of memory that can be shared across the cluster. For those of you who are familiar with NVMe over Fabric, you can basically think of OmniXtend as a memory over Fabric. The details of the protocol are obviously public. They are shown, they are discussed and being published in the CHIPS Alliance OmniXtend workgroup. And again, they take the serialized tiling messages, and we put them on top of L2 frame, Ethernet L2 frames. Ordinary off-the-shelf Ethernet switch can be used, Or you can even have fun with programmable P4 switches like Tofino switch from Intel and do more specialized processing of the cache coherence packets. And a little bit about our demo and real-world results. So we have a RISC-V SoC with OmniXtend running on FPGA. You're seeing these two boards here. We are using Intel Tofino programmable P4 switch. We actually put together four FPGA nodes like this together in a cluster, bringing a total of 16 RISC-V CPUs. Each of the CPUs is running at 100 megahertz, and we did a detailed breakdown of the latency. So if you look at some of our data, you will see these very low sort of 100 nanosecond range latencies that are happening within one node. And then you'll see these jumps that are happening when we actually need to go through a switch to access the other nodes. So then we are incurring about 3 microsecond latency. We think as we are progressing to OmniXtend Silicon that these 3 microsecond latencies will become more like a couple of hundreds of nanoseconds latency for the part of the latency from the RISC-V CPU to the Ethernet switch. So we believe that overall we can bring the latency down to about 1 microsecond. We did not forget about the software support. As a matter of fact, Atish Patra and Tu Deng from Western Digital had a presentation on this on Tuesday on OmniXtend. If you haven't seen it, I encourage you to go and check it out. In terms of software support, we did a lot of work on kernel level memory management changes. And we did this jointly with other members of CHIPS Alliance like Sci5. In option 1, we are supporting a single kernel instance. Basically, this is a very traditional NUMA SMP, CC NUMA SMP-like system. All nodes are controlled under a single kernel instance. And this is very appropriate for small-scale systems. Think if you want to scale to 4 or maybe 8 RISC-V CPUs. The nodes are exposed as NUMA nodes. The second option is a little bit more modern. It brings independent kernel instances per node, and it's appropriate for larger scale systems. In these systems, applications can share memory through a file system-like interface, basically through memory map files. So this is interesting because you can bring together future RISC-V system that could be running different operating systems. You could have Linux, Android, Windows, all running on the same OmniXtend network where you can coherently share memory. We have implemented support for the single kernel image, so the prototype is out there. I think Atish and Tu showed more details yesterday. These are mostly OpenSBI modifications with very little kernel changes needed. This boots successfully on FPGA prototype hardware. We have 4 nodes with 4 hearts each, bringing to the total of 15 RISC-V hearts, as you can see on the inside. Independent kernels implementation is currently under study and currently under development. We do have a QEMU-based emulation under development as well, and this is all happening in the open source. All right, so now in terms of the next steps. Well, number one, the OmniXtend reference design has been standardized and developed inside the CHIPS Alliance. And the Allegro files are available to the CHIPS Alliance members. And OmniXtend is very well positioned to grow. It's an open source collaboration to drive the development, and CHIPS Alliance is open to all organizations. And as I said, the reference designs are available to CHIPS Alliance members. And finally, to sort of summarize and bring some news, first, OmniXtend is an open unified memory fabric. We are proud to announce that we are collaborating with RISC-V on building joint work groups that was standardized on both TiLink next generation cache coherence protocol and OmniXtend for the multi-core systems. And we invite you to adopt the technology in your next SoC. And this is very interesting because it's going to enable heterogeneous RISC-V systems to share the common memory. To see more, go to www.chipsalliance.org. Thank you very much for your attention.